Okay, for these exponent rules, as I said on the very first day, we talked about it. And you can go back to my videos to look at it again. Okay. I actually took time to explain it because this is how our brain works. Without explanation, your brain would not like it, your brain will reject it. And for some of you, if you say, I have memorized it, but somehow I just confused myself, because when there's no example to validate your memorization, your brain is a mess. There's no organization, there's no boundaries. So we say this, a to the m power times a to the n power, it's equal to a to the m plus n. So I hope you don't just stop right here and say, oh, I just gonna memorize the rules. I hope you don't, because you should have an example such as 2 to the third power times 2 to the fourth power, it's equal to 2 to the seventh power. And as you know your examples, I hope you're not just memorizing, you're actually understanding the meaning behind this rule, so-called rule, is that when you have 2 to the third power, it's 2 times 2 times 2. 2 to the fourth power is, well, 2 times itself 4 times. So how many 2's are multiplying together? There will be 7 altogether, right? And that also proves a couple of things. First, you understand why these two exponents are added together, number one. Number two, a very common mistake that people make is that somehow they multiply these two numbers together. We had those. And how do you tell yourself that that is not going to happen? Well, look at the meaning. But again, if you don't understand the meaning, if you don't have a good, simple example to prove yourself, you are going to forget it. And I say this because it was me who memorized it without explanations, and I constantly, either applied the wrong rule or just thought that I knew the rules and that it was a total mess. And you also have to understand one thing, and that is usually if you know the first one, it leads you to the second one, such as this. If you know the first one, chances of you knowing the second one is very high. Because if you know something is adding, then the other one must be subtracting. Okay?
Over, you subtract them.
Mm-hmm. And again, you've got to know why. With a good, simple example. Why would this equal to a to the second power? Is because of this. Put yourself in the shoe that you are about to teach somebody. And somebody's going to challenge you and say, why? Let's settle this today, now, so that we don't have to come back and revisit this, because it's no fun to revisit the thing that we learned back in Algebra 1 again and again and again. Okay? Other rules such as this. That becomes, that's multiplying. And again, you better have an example to back yourself up. Something like this. I like to use 2 and 3 because you give yourself a good moment to think whether or not if it's like, is it 5 or is it 6? All right. And then you say, well, I know what cube means. Everybody here knows what cube means, right? It means that this thing is multiplying by itself 3 times, which is how many a's altogether? That's why we are having a 6. That's why it looks like a multiplication. And to be even more creative, let's adopt this perspective. If you could, that would be fantastic. Think about you actually don't we actually don't have any of these rules. We don't. We just have some examples on the right. And you look at these examples, you've discovered a pattern. And you thought like, oh, wait, hold on. I think we can create something here. We can create some rules. You can put yourself in that position and think like this. Okay? And then, now, here's a very, very common mistake. What's a to the negative m power? 1 over a to the m power. When you put the item right here to the reciprocal, that means you have properly executed the meaning of the negative exponent. And therefore, when you put it into the reciprocal, the negative sign in the exponent will be gone. Some student, which is, I think they are too panicky in thinking about this, they saw this and they wrote this down. Then I would say, what do you do with the negative? How come there's still a negative right there? And this is my point the whole time. You are writing equal signs. You're supposed to write equal signs. They should go back and forth. Are they really equal to each other? And we say, nope, that's not right, because after you put it into reciprocal, that's the meaning of the negative exponent. It shouldn't be there again. A good example would be, for example, a to the negative 2 would be 1 over a squared. And what if somebody comes here and challenges you and say, well, how do you know? How do you know a to the negative 2 is 1 over a squared? And you can say, well, here we go. Consider this. What did we say about division? When you have the numbers in the same base, but different exponents, you will subtract, right? So in this case, you can see how it is going to turn out to be a to the negative 2 power, right? But then we're like, oh, yeah, sure, it's a to the negative 2. We know that. But let's go ahead and show the work. You go home tonight, give yourself 15 minutes and ask yourself, can you list and explain these rules? If you can do it, you're good for life. Can you do something tonight that will set you for a good, successful path for the rest of your life? Just 15 minutes. Okay? This is better than Geico. This is not 15%. This is like a lot of percentages for the rest of your life. Your future tests. Okay? So, again, the basis would have to be the same. The basis would have to be the same in order for us to communicate the exponents, because that's what the meaning is. If the bases are not the same, they cannot, you cannot do anything, we cannot do anything with the exponents.
So when would you multiply the bases? You never multiply the
Never, ever, ever, ever multiply the bases. Okay? And again, we will do a lot of things intensively with exponents towards the end of the semester. Right around late April, early May, we have, that's our last unit. So again, you set this, like you settle this right now, lots of benefits. You don't settle this right now, you get buckets of tears. That's 2 cubed times 3 cubed. That's what it is. I mean, if what's the outcome? You just go ahead and evaluate each individually, but there's nothing you can do with the exponents. Nothing. You just go ahead and say, well, 2 cubed is 8, 3 cubed is 27. Just multiply them all. Okay? But in terms of exponents, there is nothing you can do. All right? Never, because the bases are different. And you know, I'm glad that you bring up that example. How do you test if you're really good? Give yourself this kind of example and say, well, this is usually how people mess up. Okay? They want to do something and you've got to know like there's a boundary and say, well, there's a boundary and you do not go across the boundary. You have to have a good narrative and say the bases have to be the same in order to operate anything.
So if it's 3 cubed times 3 cubed, then you do.
Well, 3 cubed times 3 cubed, 3 cubed times 3 cubed is 3 to the 6th power. Because now, what I'm going to say could sound a little bit crazy. What I want you to see is this. When the moment you see 3 cubed, you can also see this in front of you. Okay? And that's how you can justify yourself that, oh yeah, 3 cubed times 3 cubed, it's 3 to the 6th power. Nobody should ever mess it up. Okay? So, I hope this is the final time that I will have to explain exponent rules. Okay? You can find this anywhere. You can just go on Google and search it, but it's not that you need to memorize the rules. It's the fact that you need to understand where these rules come from.